And I suggested that we invite Professor Van Allen on Engineers Day, believe it or not, to come to the university and tell us about the discovery of the radiation belts. So he so happened that he stopped by my bench as I was working, and he says, "What are you doing?" And I said, "Oh, I'm building an ion chamber." He says, "What's this?" And he said, "Have you thought about grad school?" A year later, I found myself as a first-year graduate student at the University of Iowa, and that's how my sort of more direct involvement in the space program became possible.
Episode 99. Professor Stamatios Krimigis, exploring the solar system with Voyager. Professor Stamatios Krimigis is perhaps Greece's most experienced space scientist. He started studying physics at the University of Minnesota in the same month that Sputnik was launched. A chance meeting with James Van Allen led him to build instruments for Mariner 3 and 4, eventually becoming a principal investigator for the Charged Particle Instrument on the Voyager program, which was initially known as Mariner Jupiter Saturn 77 program. In this episode, recorded in Athens in July 2022, he speaks about his remarkable career, guided in large part by a chance meeting with his mentor, physicist James Van Allen. It is released today to mark his 84th birthday on September the 10th, tomorrow.
Professor Stamatios Krimigis, first of all, can I say it's been a wonderful but very hectic experience of the week of COSPA here. I need to congratulate you and all the local organizing committee. It's been a terrific time, a very intense time, very deep and heavy science. Well done and congratulations to all of you.
Well, thank you very much, Mr. Singh. I'm very pleased that things seem to work well, because one never knows, no matter how much planning you do, whether everyone will do their own thing and do it well, and so that the whole can work. And so far I've heard good comments from many of the participants, and of course people like you. So we're very happy that this day came, in the sense that today is the last day of the meeting, and as for myself, I'm still standing, but I am looking forward to having a lot of sleep next week and the week after when I go on vacation.
Terrific. Now, you have an extraordinary set of experiences throughout your life in probably active involvement in many of the space missions. What I want to do for the next 25 minutes or so is really just talk about your experiences from the early days and your recollections of some of the people that you worked with. And there have been really some people whose names are associated with the early days of space travel and space exploration. Let me start off with 1957. The launch of Sputnik. You were a teenager then. Is that what motivated you to get into space science?
No, I happened to be a freshman at the University of Minnesota my first year at the Institute of Science and Technology of the university. And when Sputnik was launched, a month after I started school, and all of us were, all the students were absolutely amazed and curious, to say the least, about this round sphere that was going over the United States at 900 kilometers altitude, and was going beep, 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 and nobody could do anything about that. And of course, at that time, it was at the height of the Cold War, where a lot of people were actually building shelters, underground bomb shelters, to survive a nuclear attack, which could happen presumably at any time between the United States and the Soviet Union.
So you already decided to study science when Sputnik launched?
Yeah, I had decided to I signed up at the School of Electrical Engineering. However, within about a year, I had the good luck of taking in my course on atomic and nuclear physics. I had an excellent teacher who was so I would say inspiring that I decided to switch to physics immediately, and ever since I was there. And then within a year I was able to get a job with a group under Professor Winkler of the university, who had a campaign to fly instrumented balloons at high altitude, so he could study the so-called solar cosmic rays, because at that time we knew the sun was active, but the observations from the ground were not sufficient to know anything more than what is in the optical wavelengths. And I met many very nice and helpful people there, good teachers, including Bradford Bravsar, who was a postdoc with Professor Winkler, and he was working with the balloon program. Who later, I believe, became head of the space agency in India.
Yeah, he was there for the launch of the very first rocket from India into space. Let me just take you back to Sputnik. Just like the International Space Station, it's in low Earth orbit. Sputnik was visible just before sunrise and just after sunset.
Right.
Did you see it?
Actually, I can't say that I did. I mean, being a student, you didn't have access to facilities, or at that time the information was very sparse. You could only get it from newspapers after the fact. There was no internet, so I didn't. But we had heard the recordings of the beep as it was going from the TV channels at the time. But we had a lot of curiosity, and of course, the first American satellite was launched on January 30th of '58, just 4 months later. And it so happened that Professor Van Allen, who was a professor at the University of Iowa, only 300 miles south of Minneapolis, was the person who had instrumented the first and second and third American satellites. And as is by now well known, he was able to identify the presence of high altitude radiation above the Earth. And when the announcement came in 1959, it was dubbed the Van Allen belts by the press. I have to say, he himself never called them that.
Really?
And so I was with the student council at the Institute of Technology, and I suggested that we invite Professor Van Allen on Engineers Day, believe it or not, to come to the university and tell us about the discovery of the radiation belts. And he was kind enough to accept. He came to Minneapolis, gave his talk, and then Professor Winkler took him to the laboratories to show him around about the equipment that was being built for balloons, as I mentioned. And my specialty at the time was to build something called an ion chamber, which was a detector that presumably could also detect all kinds of radiations, from X-rays to electrons to protons. So he so happened that he stopped by my bench as I was working, and he says, "What are you doing?" And I said, "Oh, I'm building an ion chamber." He says, "What's this? How does that work?" And so, being a second-year student in physics, I tried to explain to him as best I could. I think I was a third-year student in physics at the time, and he said, "Have you thought about graduate school?" And I said, "Yes." I said, "I have, but I don't have any money, so I think I'm going to try to get a job after I graduate and see if I can make some money so that I can save it to go to grad school." And he said, "Listen," he says, "why don't you apply to the University of Iowa?" And I said, "Well, sir, if you say so, I will." And so a year later, I found myself as a first-year graduate student at the University of Iowa, and that's how my sort of more direct involvement in the space program became possible.
That's an incredible story. So you ended up in grad school because of James Van Allen's conversation. Just a step before that, what took you from Greece, where you had been a school student, studied at school, to the USA in the first place?
Well, you know, all kinds of coincidences. My father was an immigrant in the United States, and when he retired and came back to Greece, and he didn't last very long, it turned out, because his health was compromised, but he had left a little money for me to go to the States.
I see.
And he said, "Listen, you have to understand that the Athens of antiquity is now the United States. So I would like you to go there and go to the university." Where to go? It so happens that my mother's sister and brother were both immigrants to the United States in Minneapolis. So there was no question as to where I would go. And that's how I ended up at the University of Minnesota, and then, of course, Iowa, as we were saying before.
So you ended up in University of Iowa. Did James Van Allen, was he your teacher at some stage?
Oh yeah, he was my mentor, and I did my master's thesis there, and within a year and a half, after I passed my master's exams, he called me to his office, and he said, "Hey, how would you like to be a co-investigator on our instrument on Mariner 3 and 4? Now, Mariner 3 and 4 were the first American or anybody else's missions to Mars. And I said, "What do I have to do?" He said, I would like you to build a detector system that can differentiate between protons and electrons. And at that time, it was significant because the radiation detectors, by and large, were the kind of instruments like Geiger counters, which would count X-rays and gamma rays and electrons and protons, and by and large didn't know what kind of radiation that was. So I said, "I'm not sure I know how to do that." And he says, "Well, don't worry, I'll help you." And I said, "Then when is the spacecraft being launched?" He said, "Oh, in about a year and a half." So anyone who is working today on a mission will say, that must be crazy,
Yeah.
because it takes 5 years to plan a mission and 5 to 10 years to implement it and get the data back and so on. That's not the way things worked at the beginning of the space program, at least not in the United States. You could design an instrument as a graduate student and do your thesis from the results. So anyway, it was a tough assignment, but somehow I was able to succeed, and we had an instrument that went up on Mariner 3, which never got to Mars. It was a failure.
Right.
And Mariner 4, which did, and of course the objective is to see if there were Van Allen belts at Mars.
Oh, okay.
And lo and behold, we got there, and there was nothing there.
And that's scientific data, that's valuable. The fact that there was nothing there didn't mean that there was
Of course. We learned that not every planet has a radiation belt. Not every planet even has necessarily a magnetic field. And turned out that Mars had a very weak magnetic field from ancient magnetic field that was kind of preserved on the ground, but really didn't extend very far into space. So you couldn't have radiation belts.
And so your career, you really were there at the outset. The very
Pretty
first.
much. That's why I said I was lucky. But we did discover things on the way, mind you. For example, with the detectors that we had, it was possible to look for radiations on the way to Mars. And I was in Pasadena at the Jet Propulsion Laboratory one day watching the data, and I saw that there was something strange happening in the response of the detectors, and I called Professor Van Allen and I said, I think we are seeing electrons from the sun, but no protons. That was the discovery of energetic electrons emitted in solar eruptions. By the end of the year, we wrote a paper and published it about the discovery of energetic electrons from solar flares. Had nothing to do with Mars, but it was a terrific discovery nevertheless.
And that was exactly the question that James Van Allen had asked you when you were at your grad school project. And can you tell the difference between electrons and protons?
Obviously, that was on his mind.
Yes. And so the reason why you have to go into space to detect these particles is because they never make it to the surface of the Earth.
Of course.
You mentioned high-altitude balloon experiments before you ventured into space. Were you involved in the balloon experiments as well?
Well, that's what I was building one of the sensors that we were launching on the balloon experiments.
Right.
Yes. And we students were essentially doing the campaign of going and launching the balloons from an old airport north of Minneapolis called Anoka. And at that time there were observatories around the world that would be watching the sun, and when they saw an eruption, they would send a telegram. and we would get a telegram, at 2 in the morning that there's a solar eruption. And we got out of bed and ran to the laboratory, picked up our equipment and the balloon, and ran out to the airport and tried to launch it as quickly as possible so we could perhaps catch the eruption, and we were able to discover X-rays.
Right.
X-rays are not prevented by the Earth's magnetic field of getting to the top of the atmosphere. You see, that's easy, or gamma rays, but electrons and protons couldn't possibly get in unless they had huge energies, because the magnetic field of Earth would prevent them from ever getting close enough.
And just a question about the equipment you're using. So these balloons, were they able to transmit the data when they were launched, or did you have to collect the instruments after the balloon had come back down to the Earth?
Actually, we had the transmitter on the balloons, and we could actually receive data, but we were also recording data because after a certain amount of time, when the battery was exhausted, we would cut off the balloon. With a little parachute, the payload would land in some farm in North Dakota, for example, and a note to whoever found it to send it back to us to Minneapolis, to the university. And we recovered a lot of this the equipment and used it again.
And did you lose any in the process?
Oh, we did, yes, of course. I mean, you know, something may well have ended up in some inaccessible place or the bottom of a river or whatever. And we would never recover it. But we did recover a fair amount because people were very kind and they said, oh, from the university, yeah, we'll send it back.
So you mentioned the name of Professor Praful Bavsar.
Yes.
Now I spoke to him about his experiments in balloons. You worked with him quite a lot?
Well, he was part of the same group.
Right.
So I saw him practically every day. I was working as a student at the laboratory, and was very energetic and very articulate, and I learned a lot of things from him, I have to say.
And another member of the Indian Space Research Organization and the former chairman, sadly we lost him a few years ago, was Professor U.R. Rao. He had an interest in cosmic rays. Did you spend much time with him?
Yes, indeed, because I also did my thesis on solar cosmic rays, they were called, but we don't call them that anymore. Energetic particles from the sun, because cosmic rays are coming from outside the galaxy to the solar system. And so he was a member of a group in Texas at the university there and in Dallas. And they had a detector on a spacecraft called Pioneer. And that spacecraft detected protons from the sun. And so, and we had also detectors on other spacecraft as well from Iowa. And we were comparing data a lot of the time, and they had he was working with a group that was, I think at the time included Ken McCracken from Australia, and eventually, you know, McCracken went to back to Australia and became head of CSIRO, and URO came back to India, went back to India. So yes, we have known each other for many years, and I remember the last time I saw him was when I was at the COSPA meeting in Mysore, I think.
Oh yes.
And we had dinner together. I mean, he's a very nice gentleman, wonderful person. And so I had known him, and I consulted with him about the program when I was the head of the space the laboratory at Johns Hopkins University over the years.
And he worked, just like you did, in many different teams, different places in the US. Did you ever go in to visit India and the Indian space?
Well, only in the context of meetings. And I had been to Hyderabad and to Mysore.
Right. And I'll just mention two other names from those times. They're a little bit older than you, so you may not remember them. There was Theodore von Karman, who has a unique place in space history. Did you ever meet or work with him?
No, I never met him because he was kind of a previous generation, if you like. But I was very happy in, I think, 2017, the International Academy of Astronautics gave me the von Karman Award, which is their highest award that they had.
And that's just one of many awards that I know that your work has attracted over the years. Robert Millikan was another individual who did a lot of work.
Again, you're mentioning some names that were of a previous generation.
Yeah.
And I know all of them, but by the time I got into physics and at the professional level, so to speak, they had all gone.
Yeah. And just one other name which you may not know very well because he was not really in your field, but Frank Molina worked quite a long time.
Frank Molina was associated, I thought, with the group in Dallas at one time, and then was he at the University of California, San Diego, or someplace. I met him in the activities of the International Academy of Astronautics when I was elected a member. And I remember him, but he was, as you say, not in my field, so we had more of a social rather than a professional interaction, except in the context of the academy.
So the one person I do want to speak to you about, and I know you know him well, is Ed Stone. Ed Stone and you and many others worked on, I think, perhaps for me, for my generation, a pivotal program called Voyager. Voyager 1 and 2 were launched 45 years ago. At what stage did you get involved in Voyager, and when did you meet Ed Stone?
Well, actually, I had met Ed Stone before Voyager. He had gotten his PhD at the University of Chicago, and excuse me, we had then a series of meetings which was called the Midwest Cosmic Ray Conference. And we would gather from universities in the vicinity, but also some from the East Coast. And I had organized in 1968 the Midwest Cosmic Ray Conference at the University of Iowa, just before I left to go to Johns Hopkins. And Ed Stone came there to give a paper. He had already gotten his PhD some years back, and he had moved on to Caltech. So I knew Ed. We were generally in the same field. And then in 1970 is when NASA announced its intention to do what they called the Mariner Jupiter-Saturn program, which was a spacecraft that would go to Jupiter and Saturn and investigate those. And I was on the mission definition committee. Ed was, my recollection is he was not a member of the committee, but then once the program was approved by NASA, he was appointed by the Jet Propulsion Laboratory as project scientist. So, and I was lucky to have been selected as a principal investigator for the low energy charged particle instrument. So that's when we started working together sort of continuously since I think 1972 when we began to build the instruments and have regular meetings. And so you said past 45 years, more like 50 years now, since we started, because you know, you get to work on a program long before it gets launched.
Of course.
And of course it was in the process that we changed the name once we finished the spacecraft. A few days before we launched them, we changed the name from Mariner Jupiter Saturn 77 to Voyager. So that's how the name came about. And of course, under the leadership of, with the leadership of Ed Stone, we always kept in mind that if these spacecraft were to last more than 4 years, we could go farther out to explore the outer solar system and perhaps someday get to the termination shock of the solar wind and the so-called heliopause and get out into the galaxy.
So you had considered this possibility prior to launch?
Yes, we did, because we knew that we could do it dynamically with the gravity assist from the planets. And the only issue was that at that time, nobody had built the spacecraft that would last 4 years, let alone 45. So it was kind of a dream. But then once we got past Saturn, and then we directed Voyager 2 to encounter Uranus and Neptune. We got there in '89, and the spacecraft still were working very well. We decided to request permission from NASA to approve a mission called the Voyager Interstellar mission, because that was going to be our goal from then on. But please note, it was 1989 after we passed Neptune. And we said, by golly, you know, sooner or later we're going to cross a boundary into the galaxy. Little did we know that it was going to be 23 years before we ever saw the boundary, which came in 2012 for Voyager 1 and in 2018 for Voyager 2. So all of this was, you know, uncharted waters. You couldn't know any of it.
Exactly, and it was powered by a radioisotope power source, so although it's getting further away from the sun, the power would be decreasing, but the idea that it could still remain in contact with the Earth, I suppose that required some development at this end at low energy amplifiers, so that you can detect fainter lower power signals from far away. So the technology has been growing as its power source is decreasing, at a distance it's been increasing. So it's remarkable that it is now beyond the heliosphere and still in contact. Are Voyager 1 and 2 in contact with the Earth regularly?
Oh, it happens every day.
Every day?
Yeah, but we need a big antenna. As you pointed out, you know, there were a lot of improvements on the ground in major amplifiers and such new technology that decreased drastically the noise of the system, so that we could actually track and receive data from Voyager after all these years. So it was a combination that we learned how to fly the spacecraft and make some improvements, if you like. But the big change was on the ground. The ability to track and receive data from Voyager at these distances. And as I was pointing out yesterday, I guess we have 160 bits per second from the interstellar medium at a distance of 23.4 billion kilometers, and it's not a problem. If we had enough power on the spacecraft to keep it alive and keep the instruments working, then we would go for probably another 20 years. But unfortunately, as you point out, we had these radioisotope thermoelectric generators, which utilize the heat from radioactive plutonium-238 to generate electricity. So we're now, instead of 260 watts, we're now at 230. Needless to say, the mission was never designed to last that long, and we have to make all kinds of adjustments to the instruments. In my instrument in particular, we have a little stepper motor that rotates every 192 seconds to scan the whole sphere.
Right.
And it's a very important measurement to us, and it led to a lot of discoveries because on a spacecraft that's always pointing at Earth, you don't get to look in other directions unless you do it yourself with your own instrument. And that stepper motor was designed to last us through Saturn.
Right.
For 4 years. And we only tested it for, I think, 500,000 steps. And so now it's past 8 million steps.
Wow.
And it's still working. The most amazing part, however, is that 2 years ago, when we had to decrease, turn off essentially the supplemental heater, the temperature of this device went from -10 to -60, and it's still stepping.
Right.
I was absolutely astounded by that. It's needless to say, we never tested it for that temperature. The fact that it's still working, I don't know what to attribute it to.
The Voyager team, there's not many, as many left, of course, now. It is 50 years ago that the program first started. Do you keep in touch with many other members of the team, including Ed Stone?
Yes, of course. We still have the so-called science steering group meetings twice a year.
Right.
Needless to say, the last 2 years, because of COVID, they were Zoom-type meetings, remote. But yes, we are in regular communications. Mind you, some of the members have passed away. And but as I was saying yesterday in the press conference, we have younger people who we're bringing on. But there are special problems. For example, when we needed to see what the effects on the instrument would be at these temperatures. We had to go back and to look at some of the initial circuit diagrams and so on. And everybody today says, oh, what's the problem? You know, you just get to the right file and bring it up. And no, at that time, all the files were paper. And the circuit diagrams were stored someplace, and some of them have been destroyed. So we had a very hard time just getting the documentation, let alone the people who did some of the designs of the detailed electronics to tell us what would happen if we did this or if we did that. And so my principal value to the project is that I'm still alive and I remember some things.
I mean, it is an incredibly eventful life experience you have. Just a question about, to bring it back up to date, in Greece, this science and space science is flourishing, and now we have the Hellenic Space Agency established. What impact do you think Greece is playing its part in the world of science, and particularly the space age, as it should now?
That's an interesting question. I think Greece was very slow as a country to really get into the space program per se. That's not to say that Greek scientists didn't get into the space program, because as everyone probably knows there is a big Greek diaspora in Europe, the United States, mostly those parts of the world. But many of them are actually quite prominent in their own fields, and so Greek scientists and technologists and engineers have contributed a lot and are working in the space program, but not in Greece. So the job for the Hellenic Space Agency, Hellenic Space Center, is to put together a coherent enough program to attract the kind of people that they need to make rapid progress. And they're at that, and they're trying, but they have a long ways to go. There is some small companies that are working in the space program that have specialties that are workable and competitive, and they get some programs from the European Union mostly. So there is some level of infrastructure that could be taken advantage of, but it has to mature, and that's the job of the leadership of the agency. It's only 2 years old, basically.
And if I can ask you, and this is perhaps difficult to assess at this point, what impact do you think this last week has been to encourage the Greek government, the Greek Space Center, as you say? I know from the contribution you've been making, showcasing Greece and its capacity to be a more active player in space. I got the feeling that as a result of this week's and your contribution, and many others of course here in Athens, that it's been a bit of an impetus. There's a bit more momentum and inertia behind the space activities.
Well, that remains to be seen, but I hope that it is indeed, it is having an impact. Among other things, the Prime Minister asked me to see if we could get the heads of space agencies to his office, and he received us on Monday. And of course, he's a very modern man and well educated, and he was asking us all kinds of questions about programs, where James Webb is a big deal these days, but about other things as well. So, if nothing else, in his sort of screen, there is something called space. And that the fact that many of the countries of the world came to Greece to have their meeting and discuss science and technology, I hope is having the right kind of impact, but most importantly, about the young generation. That's what I was hoping to be an impact, and it is indeed having an impact, both in the social media and in the press. And so many of the young people see this as not beyond the reach of the small country like Greece, and they see that either through the local technological establishment or through the diaspora, they can really have a future in this business. And I keep telling them when I give a public lecture that we have to make the future, not wait for it to come to us.
And I have noticed that strain in just about everything you've been saying. So in conclusion, I assume that you are hopeful and optimistic that soon, either on its own or through the European Space Agency or other partners, Greece will play a more active role with launchers and building their own large satellites, and perhaps even Greek astronauts in the years to come.
Well, Your words were hopeful and optimistic.
Right.
Yes, I am. But it's not going to be done without hard work and determination and a plan, and those are the things that are yet to be demonstrated.
Well, I think the fact that you worked on Voyager, and it is perhaps one of the most impressive and iconic accomplishments, technical accomplishments in my generation. I'm sure from your efforts, Greece will be achieving unlikely things in the future with as much daring as you have demonstrated throughout your career. Professor Stamatios Krimigis, thank you very much indeed. Appreciate your time.
Thank you very much for inviting me to this discussion.